We are going to be looking today at evaluation of translation. Really, it's slightly more general than that. It's really evaluation of generated text. But let's just look at it in the context of translation for the moment. So we know when we're training our neural network that we're going to try and train it to generate the exact Y, that is the exact translation we have in mind. But when you have gone ahead and trained some English to Spanish translator, and then you want to evaluate and say, how good is this translator compared to other translators, you want to have some metric that you can use, some apples to apples metric. So what metric do we use, let's say, for categorization? If we're trying to see, how good is VGG versus ResNet versus SqueezeNet, what might we use, let's say, for ImageNet classification, where we've got 1,000 categories? So what might we use?
Wait,
And what is used?
sorry, what will we use for
Yeah, we're just trying to see how good is VGG, right? I trained this VGG network. How good is it?
well, the labels would just be like if it's binary, then it's just like whether it is like a certain thing.
Okay, so we've got 1,000 different classes, right? And so we can look and say, we can use basically accuracy. We can just look and say, right, we've got, I don't know, some test set that we're using or some validation set, and we want to see how many of these did it get right? That is, that the highest probability was the correct class. So this would be top 1 accuracy. And do you remember, I think we talked briefly about top 5 accuracy. Right, top 5 accuracy says you had your highest probabilities that your model predicted, or let's say it predicted with 0.6 that it was a grizzly bear, and 0.3 that it was a brown bear, and 0.05 that it was a Dalmatian, and so on, right? And so the top 5 says we're going to look at your top 5 predictions, and we're going to say that we're going to consider it top 5 accurate if the correct answer was one of these. Okay, so that's obviously, it's easier to be top 5 accurate than it is to be top 1 accurate, right? And we wouldn't want to do this if we only had 5 classes, right? Because then top 5 accuracy, everyone gets 100%, right? Because they're predicting all 5 of the things with some probability, and so they would all win. So if you only had 5 classes, it wouldn't make sense to do top 1 accuracy. But if you have 1,000 classes, maybe top 5 accuracy makes sense. What's important to know is once you've defined a common metric and a common test set, then all of a sudden it's easy to have things like competitions, easy to see what progress is being made in attacking this problem, because everyone is on the same level playing field. That is, they're all dealing with the same data set and they're all evaluating it in the same way. So that's how the ImageNet accuracy, first the top 5 accuracy got better and better, and then actually the top 1 accuracy got better and better again until it became better than human accuracy. So for translation, it's a little bit of a harder problem in the sense, what is a good metric to use, right? So this is 2 different metrics. Some of you did, if you remember back to lab 2 where we had the rotation, okay? And one of the challenges was to do a regression problem, so that instead of a classification problem where you were trying to predict from an image either 0, 90, 180, or 270, Instead, the regression problem was, given an image, generate x degrees, how many degrees it was. Here, in the 0, 90, 180, 270, the metric is pretty straightforward to use, right? We would just go ahead and say, what's the accuracy? In the regression problem, it's a little unclear what it should be. I mean, accuracy, what is accuracy at? Does accuracy mean exactly the same floating point number to 100 decimal places, or however many decimal places we have? Does it mean to 1 degree? And so in fact, for those people who did that challenge, what I suggested was go ahead and make a couple different metrics, you know, within 5 degrees, within, 10 degrees, because these are something people can understand. What if I wanted to have a metric that measured the same sort of thing as this? So I wanted to measure that you got rounded, you got to the nearest 0, 90, 180, or 270. You got to the correct 0, 90, 180, or 270. What would I use as a metric?
So if we were to round the prediction?
If we were trying to measure the same sort of thing here, which is here, we were just trying to measure, did we get the correct 90-degree rotation?
Mm-hmm.
Here in the regression problem, right? So this is regression, whereas this one was classification. I want to know if I went ahead and rounded the degrees I've got to the nearest 90, that I matched the rotation of the input image, right? So let's say I know the input images are in 90-degree increments, and then I want to make sure my regression, I round to that as well.
So it seems like you're almost kind of making it a classification problem again. So
you're kind of turning it back into a classification problem. My claim, though, is that's the same as leaving it as a regression problem and having within some number of degrees.
Okay, yeah, so just within, I guess, 45.
Yeah, if you took it within 45 degrees, then you can actually compare sort of apples to apples. How did this do as a regression problem compared to how it did as a classification problem? So coming up with these metrics can matter, and we're going to now talk about a metric for language translation. Normally, the way language translation was done was having humans evaluate, sorry, not how language translation was done, but how evaluation was done, was have humans evaluate how good are these translations, right? So you'd have a human, the human would go, they would look at the source that was being translated, they would look at the target that it was translated into, so look at the original English, look at the Spanish, and then say, how good a translation is this? Okay. Some problems with that are, I don't know, come up with some problems.
I guess it would be like subjective.
It's subjective, yeah. So you might have two different evaluators who didn't agree. One of them might be a harsh grader, right? And one might be a lax grader. So, you might have some levels of translation, excellent, let's just say A, B, C, D, and F, okay? And there might be some differences in what a translation is graded. One person might grade it an A, another person might grade it a B. Hopefully, we're not going to have one person graded an A and another person graded an F, right? And if you had two very close translations in quality, there might be a difference in the ordering, right? One translator might say this one's better, and the other of a pair, and the other translator might say this was better. But if they're fairly different in quality, then one would hope they'd both agree on the relative ordering. Okay, so problems with human evaluation. We would have interlinear I'll just call it interhuman consistency. What else?
It's hard to quantify.
It could be hard to quantify. If you went ahead and had people grade it from A to F, then that could probably give you some measurement. But you would need some way to quantify it. Right? You still need a metric. It's not enough to just say humans are going to evaluate it. We don't want them to give a written narrative about the evaluation. We do need some sort of a score. So we need to define a metric. As well as interhuman consistency, we might have intertemporal consistency. That is, a given human might rate a particular translation differently on Monday than they do on Thursday. All right? So if you do it again, you might get slightly different results. Give me another disadvantage of human evaluation.
Expensive.
Yeah, it's expensive. And one that kind of goes along with that. How long will it take? Right? Could be slow. So for all these reasons, some folks at IBM in 2002 came up with this bilingual evaluation or evaluator? Evaluation, I think it's evaluation understudy. Understudy with this theory that unlike humans, who are going to just, all they need is the source and the translation, and they can tell you how good it is, the understudy gets some additional information. So the understudy is going to get provided the target translation. They're going to get provided the candidate translation, the one they're supposed to evaluate, plus they're going to get a bunch of, or a set of human translations. So existing high quality human translations. So BLEU is going to get given several high quality human translations. And they're also, the BLEU is given this metric. Really, it defines this metric. So it's not even quite clear to say it's given, but let's just say it's not even given. Let's say it defines a metric. So it's given several high quality human translations, and then it's also given a target translation or a candidate translation. And then it is going to programmatically compare and say, given I don't even care what the original sentence was. So I don't care about what the English sentence was. I'm going to just look at the Spanish translation, look at some other Spanish translations, and somehow get a sense of how good this candidate translation is. So it's going to define a metric between 0 and 1. 1 is going to be what it's going to consider a perfect translation, and 0 is going to be an awful translation. So the advantage of this is you come up with a new translation algorithm, right, using neural nets or not using neural nets, but you come up with a new translation algorithm, and then you can easily, assuming you have a data set of these high quality human translations, you can then go ahead, a data set of English, assume we're doing English to Spanish. So you have a data set with a bunch of English sentences and a bunch of human translations. Run your English sentences through whatever your algorithm is to come up with your candidates, and then score your candidates based on BLEU. And then you can say, what's my BLEU score compared to state of the art, right? So state of the art might be 0.53, and I come up with a new deep learning architecture that comes up with a 0.59. So I have now exceeded state of the art, and I'm the new state of the art translator. So we are not using this for training. For training, we're going to use the mechanism we just talked about slightly earlier that Tom asked about, where we're going to be looking at the y-hats that are coming out, and we are going to be comparing those to our y, which is our, let me just write this down for just a second. So let's say we have, so this would be our training set. We'd have English 1, and then we'd have an associated Spanish 1. And by 1, I just mean it's the first sentence. So an English sentence and an associated Spanish sentence. An English 2, an associated Spanish 2. All the way to some English N, and associated Spanish N. And so when we do our training, we're going to be feeding into our RNN or whatever our translation mechanism is, our English sentence, and then we're going to be computing the loss based on the Spanish target sentence. So we're going to be seeing, did this translation actually come up with exactly these words? When we're doing evaluation, it's going to be somewhat different, right? Our evaluation is going to have some, let's say, English K down to English 2K. I'm not sure, just some number that's outside this range. So we have some range of English sentences. And then for each English sentence, we're going to have a set of K1, K2, K3, maybe K4, okay? And maybe this one has, so this one has 4 candidates. This one, let's just say they all have 4, okay? So we have English and we have 4 possible translations, each of which were done by a human. We're going to take this, we're going to feed each of our English sentences into our translation, and then we're going to compare and say, okay, that's going to give us a candidate. We'll compare it against all these human translations. We'll come up with our metric. And that allows us now to say, how well does our translation system work as compared to other translation systems out there? Or I've got my translation system, I'm working on Google Translate, and this week I've got a score of, 0.56. I've made some improvements. How much better am I doing? So we're trying to come up with this. And why do we have multiple translations? Isn't there a single best translation of any given English sentence?
There could be multiple, like, I don't know, synonyms or something.
Synonyms, I mean, you look at translations of all sorts of things, right? Translations of, I was going to say Shakespeare, but we're in English and we don't get to see any Shakespeare translations. Tolstoy, right? There are a variety of different translations of Tolstoy from Russian into English. And it's not like one of them is the best and all the others are crappier, right? There are a bunch of potentially good translations. Similarly, look at all the translations that exist of the Bible. For example, King James and all these other types, right? They feel different, and yet they are all valid translations of the original. We're trying to reflect some differences here in how humans translate, and they don't so if you got something like The Cat in the Hat, that is a very simple translation to El Gato and El Sombrero. But if you have instead Moby Dick or Hemingway, and you're translating that into Spanish, there might be a bunch of different possible translations.
Wait, I have a question. So are candidate translations like it's not human translated, right?
Yeah, so the candidate translation is going to be from machine translation. So we're going to do training. We're going to create ourselves a neural network, right? So we're going to train the neural network, and then we have our neural network, and then we're going to feed in, let's say, one of these guys into here, and we're going to get as output a candidate. And then we go evaluate this candidate, and we say, how good is it? And we feed this into our BLEU system. And our BLEU system, we're going to feed in our candidate along with each of the associated 2K1, 2K2, all the way to 2K4. Feed in all these possible human translations that we've got for it. The advantage of this, of course, is we're doing this exactly once, right? We're not having to do this over and over and over again. We get our data set, and once we've got an evaluation data set. So we want to come up with something that is, let's see, repeatable. Okay, so it's consistent over time. It doesn't have multiple humans to worry about. It's fast and it's cheap. That's our goal. Okay, so we're going to look in a moment and see how we do this. So yeah, what this is taking advantage of is really the fact that humans are competitive, and so if we have some metric we can use, we can try and break it. You know, try and break the 4-minute mile. Try and break some existing, best BLEU score for translation. And we might define, state of the art for all sorts of pairs of languages, right? So this is bilingual, so it's between 2 different languages. And so we have a state-of-the-art BLEU score for English to French, a different one for English to Spanish, probably lesser one for English to Chinese, and so on. So let's look at some sentences. So let's say these are some human translations. This is from Chinese, okay? And we don't have the original Chinese here. Okay, that's not going to be necessary for us to do our computations of this BLEU score. So we've got one translation. It's a guide to action that ensures that the military will forever heed party commands. This sounds vaguely communist, I guess. Or it's the guiding principle which guarantees the military forces always being under the command of the party. Or what is the practice? It is a practical guide for the army always to heed the directions of the party. So these are 3 different translations from humans. And then here we have some candidates. I don't know exactly how these candidates came up, whether it was machine or it just could be very poor humans, I guess. So it's a guide to action which ensures that the military always obeys the commands of the party. And it is to ensure the troops forever hearing the activity guidebook that party direct. Just which do you think is a better translation, 1 or 2?
I think the first one, because it's like more similar to the first good human translation.
Yeah, that's one way to look at this, is similarities to human translations. In fact, let's see if we can capture that somehow. So let's just look at something simple and just say what words are in the candidate translation that are in any one of the human translations. Okay, so for example, we've got, let's see, it and is and a. Well, actually, it is a and guide to action are all in the first human translation, right? Is which there? Yeah, which. Right, so I'm just kind of going to show that this occur over in here. Which occurs, let's see, here. And so we've got a which over here. Ensures, yes, right? We have ensures here. And we've also got an ensures up here. We've actually also got it is here and here. Ordering at all. I am just saying basically, does the word it appear anywhere in here? And yes, it does. And does the word is. What about that? Yes, we've got that here and that here. Let's see, the here and the, let's say, over here and here and actually here. We don't know. So let's see, the, any other thes? There's a the over here and a the here. Let's do military. Does always in? Yeah, always is in the third translation, isn't it? Is obeys anywhere? I don't see it. We missed a the. So we got another the here. Commands, yes, commands. Of the party, yeah, that phrase, in fact, is in the second one here. And let's assume we're doing one thing. That is, we're making everything lowercase. Okay? So party here and party here, we're going to assume are the same. Now, if we look at the second, so if we look here, almost every word appears somewhere here. Right? In fact, all but one of the words, obeys, appears somewhere here. If we, on the other hand, look at our second translation, then we've got what? It is, I don't think we have a to or ensure with an I. The we definitely have. Troops, no. Forever, yes. Hearing, no. The, yes. Activity, no. Guidebook, no. That, yes. Party, yes. And I don't think we have a direct. We have a directions, but that's not exactly the same word. So this gives us a sense, right, more of a numeric sense here of captures the fact that we have many more words here that are found in human translations than we do here. More words in here that don't appear anywhere in our human translations, fewer words that appear there. Or the converse, more of the words here appear here, and fewer of the words here appear here. Okay, so that's going to be our intuition for how we are going to come up with some calculation. Okay, that's not the sole thing that we're going to do, but that gets us started in our intuition. All right, I'm not going to use these translations from now on because they're too long. We're going to look at some much simpler translations. All right, so let us look at some human translations. And we're going to do cat is on the mat. That's one translation. The second translation, there is a cat on the mat. Okay, for our human ones. And now let's look at some candidates. Okay, so candidate 1. So candidate 2 is going to be cat sat on the hat mat. Okay, not a great translation. 5, 6. And candidate 1 is going to be the same length. First question, which is the better translation, given that they're both not very good?
The second one.
Yeah, I'd say the second one is better than the first one. Okay, but if we just calculate, so let's just look at a count for each word in candidate 1. So if we got the count of the, we have 3, 4, 5, 6 thes, and we have thes everywhere. So we're going to come up with a count of 6. So we have 6 matches, because each one of these thes matches, there's some the in both of these sentences. And out of 6 would give us a total of 1. Perfect translation. Okay. I'm going to say for the moment, what we're looking at is unigrams. So for the moment, unigrams, which is just single words. We're going to extend this to multi-words, but for now it's 1. So that's candidate 1. For candidate 2, we're going to look and say, candidate 1, we looked and said, each the, yep, does appear. So it's got a perfect score. Here, cat, yes, sat, no, on, yes, the, yes, hat, no, mat, yes. So what would the score be for this one? If this one is 6 out of 6, what would this one be?
4 out of 6.
4 out of 6, right. But I don't like this 6 out of 6. It seems like cheating, doesn't it? The 4 out of 6 seems like it's honestly earned. But the 6 out of 6, something's wrong. What's wrong with this one?
I guess the is appearing not at the right place in the sentence.
Yeah, the place is true, but for this one, we're not even looking at place either. So for the moment, let's ignore place and let's just look at occurrences. So is this the here seem reasonable to be getting a score of 1 for this?
Oh, I guess the number of those in the first one exceeds the number of those in the original, like the human translation.
Exactly. So how many thes in the first human translation?
1. Oh, 2.
Okay, 2. Good. You were worrying me for a second there. And the count of thes in the second one is 1. So what we're going to do is we're going to now clip the counts. Okay? So we're going to go ahead and say we're going to clip count the. So we are not allowed to have more than the maximum in any human translation. So if no human translation used more than 2 thes, we don't get credit for more than 2 thes. So our clip count of the for candidate 1 is going to be 2. And so our total score is going to be equal to out of 6, instead of the 6 out of 6 when we counted each of them. This seems very formulaic, but that's exactly what we're coming up with, a formula for this. So, and you're right, Tom, this doesn't keep track at all of the order of things. We are going to deal with that as we start getting into multiple words. So instead of unigrams, which is a single word, we're going to look at bigrams. So the bigrams in here are the cat is on the, and the mat. Trigrams are the cat is on the, and on the mat. 4grams, are contiguous 4 words together. And so we're going to extend this idea of coming up with a measure for not just unigrams. But this, let's just look at what we're going to do. We're going to take each unique word in the candidate sentence. We are going to clip count it. That is, we're not going to give it credit for more than the maximum number of that word in any sentence. And then we're going to sum them up and divide by the number of words. So we take the summation for all distinct W of clip count of W, and we divide by the number of distinct words. And this is going to be what we call the precision. Since we're using words, it's going to be P sub 1. So P sub 1, because unigrams are a 1 gram. So again, our P1 of candidate 1, there's only one unique word, which is the clip count of the is 2. I lied on this, I'm sorry. This is just the number of words. So the total number of spaces here we have. So it's 2 divided by 6 in this case, and here the clip count of cat is 1, sat is 0, on is 1, the is 1, hat is 0, mat is 1, so we get a total of 4 over 6. Okay, so that's its P1 score. You can see that the precision score has to be between 0 and 1, right? The maximum we could possibly have is every word is counting. And so we're dividing by the number of words, so that'd be 1. The worst case is our clip count is 0 for every word. And so our minimum is 0. Now we can do the same thing for P2. P2 would be the number of distinct bigrams. Let's call them X. And so we take a clip count of X and we divide by the number of bigrams. So that'd be P2. And in general, PI is the summation over the distinct igrams, counting the clip count of the igram over the number of igrams. So a unigram is a 1 gram, a bigram is a 2 gram, we have a trigram, which is a 3 gram, etc. So P1 for here is equal to 2 over 6, and P1 here is equal 4 over 6. Now let's calculate P2. How many bigrams are there? Not distinct, just total bigrams.
Do we overlap it, or is it separate?
We do overlap them. Yep.
Okay. Then there would be 5.
5?
Yeah.
Yeah, 5. Because there's 1 less than the number of unigrams. Because we start at the first, at the second, at the third, at the fourth, and the fifth, but we can't start at the 6th. I assume unless we had some sort of padding, if I make a joke back to CNN. All right. And each bigram, how many unique bigrams, how many distinct bigrams are there? In candidate 1.
Just 1.
Just one. And what's the clip count of it? How many times does the appear anywhere here?
0.
Yeah, that's 0. Now let's check P2 here. P2 equals, again, we have 5 of them, right? Because we happen to chose 2 sentences that had the same length. So cat sat. Does that exist? No, right? Sat on. No. On the? Yes. The hat? No. Hat mat? No. So this one is a yes. So we've got a 1 out of 5 here. And similarly, we could calculate P3 and P4. Okay, it turns out when you look at the paper for this, P4 is scores a pretty good representation of kind of how fluent it seems to be, because you're really capturing phrases or short parts of phrases from parts of these human translations. So the BLEU score is defined for any one of these P sub I, but we normally just use P1 through P4. So we calculate P1, P2, P3, P4. And then we go ahead and, let me just remind myself how we put these together. We go ahead and sum the log P sub i's. Okay, so for I equals 1 to 4. We use the log because the P scores are going to get, P1 is normally larger than P2, is larger than P3, is larger than P4, and so this tends to bring them down into a closer range together. How can this gamed? Or maybe another way I will think about it is, what about very large translations, right? So you have human translations that are all, you know, in the range of, for a particular sentence, 10 to 20 words. And you have a candidate translation that's like 40 or 50 words. Would you think that's a good translation or not so good?
Not a good translation because it has a lot of unnecessary words.
Yeah, probably not. Now, it turns out for the BLEU, they want to, well, do we have any penalty for that long translation? How's that long translation going to do compared to shorter translations? Can I get a score of 1 if I have a translation that's twice as long as any of my human translations?
Yeah, I guess you can create bias.
I don't think we can. And the reason is, right, we're going to divide by the number of words. And the maximum credit I can get in the numerator is my clip count of my W. I don't think it would be very easy to get the numerator equal to the denominator if I have twice as many words as I do in any of the human translations. Okay, because I'm just not going to get, there are either, right, so let's look at the possibilities. If I have a long translation, either there are words that don't appear in any human translation, and then I'm going to get zeros for those, right? And so that's going to ding my score. Or I have words that do appear in human translation, but I'm using them more. And so if I'm using them more, I'm probably going to get clipped out by them because I'm using more than they are in the human translations. So sentences that are too long, translations that are too long, are already sort of dealt with. However, translations that are too short, you can unfortunately get a good BLEU score. So let me improve my score here. Let me get myself a perfect BLEU score. Okay, so this is going to be candidate number 3. So candidate 3 is going to be the cat is on. All right. What's my P1 going to be for that?
Is 1.
P1 is going to be 1. I've got 4 words, and they all appear in human translations. Right? In fact, they all appear in the first one. So here, P1 is going to be 1. What's P2 going to be equal to? Right, so this is equal 4/4. P2 equals?
Is 1 again.
1 again, right? What's the denominator?
3.
and the numerator's 3, because the cat is, and is on are all in here. P3 equals,
1 again.
yep, 2 halves, and P4 equals 1 half. So I've got myself a perfect BLEU score. So we need to somehow add a penalty for short translations. Okay, so we need what we'll call a brevity penalty, because of the fact you can get these good scores if you go ahead and just make short translations. So the brevity penalty, we're going to go ahead and multiply by this. And our brevity penalty, so let's let C, size of C equal the candidate length. And the size of R, the cardinality of R, be the shortest reference length. All right. So then BP, we're going to just say is equal to E to the 1 minus R over C. So let's see if this makes sense. So if R is equal to C, then this is just 1 minus 1, which is e to the 0, which is 1, and there's no brevity penalty. So this is the brevity penalty, and this is if C is less than R. And it equals 1 otherwise. So let's say that R is twice as big as C. So our candidate is half as long as the shortest reference. Then this is going to be, let's say R is 50 and C is 25, right? So this will be 1 minus 2. Let's look at an example. So let's look at actually this example, okay? So the size of C equals 4. The size of R equals 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So 6. So therefore, we're going to be, the brevity penalty is going to be E to the 1 minus 6/4 equals E to the negative 0.5 equals what? 1 over root E. So that's going to be about, I don't know, 0.75? Probably less than that. Somewhere between 0.5 and 0.75, I think. So that will correctly add a penalty to candidate 3, where candidate 2 would have no penalty because it has the same length as the shortest reference. Give me an example of how you could use this for evaluating something that is not translation from one language to another.
What do you mean by something that's not a translation?
Yeah, so let's say, how can I use this evaluation to try and evaluate generated text, because it is certainly evaluating generated text, but generated text that is not a translation from one language to another?
You could use it, I'm not sure.
Okay, let's think of a task where you're trying to generate sentences. And let's see whether it can be used. So a task where you're generating sentences, but you're not generating sentences because you're translating from another language.
So something like image captioning, maybe?
Okay, image captioning. So let's look at that example. You've got a picture. All right, there's your picture, right? And this is in fact what we're going to be looking at in the next section. So this will be recorded video for you to watch. So let's say you're trying to convert this to, a house in the sun with birds. Sorry, let's not say you're trying to do it. Let's say that's what you come up with, right? That's what your machine translation comes up with. And now your question is, how good a caption is this? So one way you could do that is feed this problem to a bunch of humans, right? Feed it to 5 different humans and say, hey humans, give me a caption for this. And they would come up with different things, wouldn't they? In some sense, they're doing a translation. They're not translating from one language to another. They're translating from one medium to another, right? They're translating from a visual medium to a textual medium. But if you ask 5 different people to caption this, you'd probably get 5 slightly different captions, right? But it's not going to be totally different. This one's not going to be talking about, it's not going to be talking about robots and UFOs, I would guess. So they will have some overlap of words. One might have sun, one might have sunny, one might have bird, one might have seagulls, and so on. But still, you could get some idea if you had these reference captions to see how good your caption is. Okay, what's another generation of text that you might do?
Okay, so like, well, oh, never mind. I guess it makes sense. Yeah, never mind.
Well, go ahead. What's your question? Because other people may have it.
I just thought like, yeah, it was a wrong question. Like, if you don't have anything to translate from, but then like I thought about it, you mentioned that you have some humans to give some quality like caption.
Yeah, you got to have some humans in the loop to actually, right? You're needing for this problem. You're needing humans for 2 reasons, just like we need in language translation. You need them for training. So you need to have captioned images in order to do training. And then you also need captions in order to do evaluation. And you need multiple captions. What about this? What about you've got a large document and you want a summary? Is this a problem? Give me an example of where you might see this used, this summarization.
Text simplification.
Tell me more about that.
I know there's something like I can't remember the name, but there's like a simplified version of Wikipedia.
Oh, that's true. So there's a simplified version. Yep. There's also that's not quite a language translation problem, but in some ways it is, right? It's a translation to a smaller vocabulary and less complex sentence structure. Summarization, sometimes I think you see this in Google, I believe. So when it provides just a little synopsis, like of what a page is about, right? Is the best way to summarize a big web page just to pull out the first couple sentences of the web page? Necessarily? No, not necessarily. Or you can imagine if you've got automated headline generation, right? I've got a newspaper story and I want to come up with a headline for it. In some sense, that's a very small summarization, right, of the entire article. This as well, you can imagine you could be evaluating how good is the summary based on having several reference summaries done by humans. But I guess a key takeaway here is just how useful it is to have metrics and how useful it is to have good enough metrics that everyone agrees on. So there's certainly been some improvements to BLEU. I think there's one called Meteor that is considered to be better. But a good enough metric can really succeed in causing a lot of improvement in the field. There are metrics, for instance. Are any of you familiar with protein folding? That's a problem in biology, right? You've got a sequence of bases, and you just want to know, okay, if I've got this and I let it turn into a protein, right? So if I've got, let's say, some RNA, how will this RNA actually fold up into a protein? And that is super expensive to actually compute. And so there's a lot of work that's done in trying to anticipate how that's done. Anyway, in the last year, DeepMind came out with a state-of-the-art protein folding using neural nets that just blew away anything that had pre-existed. And part of how that's done is they have metrics for this. So they have metrics for like how far off in degrees this is from that and so on. But they have a set of metrics, and that's important to be able to evaluate the results of different algorithms. So that's it for BLEU, Bilingual Evaluation Understudy.